And so this semester is going to be about electric fields, electric forces, magnetic forces. We're going to get to optics, which if you need to review it, start reviewing your geometry now. Because optics is solved with geometry.
That was my COVID year.
Well,
did IXL.
I would pick it back up again. You're gonna learn things that already do that. Like for example, if I have a magnetic field going this way, pointing in this direction, and an electric charge enters that magnetic field, which way does it force the electric charge to move? That way. Because that's how magnetics works. Because if you'll notice, you remember looking at the electromagnetic wave? I'll speak slow. No, we did that in general chemistry.
I think I might just start showing it through this chem class too.
Do you remember the electromagnetic wave and how you had one wave propagating in one direction? The other wave was perpendicular to that, or as we call it in quantum mechanics, orthogonal.
Does it look like DNA?
Okay, you
Not really.
You do give me some.
We don't really use orthogonal in this level of class because orthogonality is an idea that means these two individual spaces, they exist completely independent of each other with absolutely no overlap of space upon space.
Look up. What do I need to look for?
Look up an electromagnetic wave and you'll see how they propagate perpendicular to one another. That means that they exist. They both exist in the photon. The photon is of course the force carrying boson of electromagnetics, but they exist in completely orthogonal spaces from one another. So they're there together, but it's like if there's a being in this room right now in the fourth dimension, like messing with your hair, you're not going to know because it's in an orthogonal space. Not in this dimensionality.
I really needed them to think. Did you watch Stranger Things?
That sentence reminds me of the upside down and straight.
You'd be surprised how similar it is. Okay, fine. If you want to do that, in Stranger Things, the real world is electricity. The upside down is magnetics. And when we get to the math of it, you will think it's the upside down.
So wait, if it's orthogonal and doesn't affect each other, why is it?
They do affect. They can affect each other due to forces. They're just not. They just propagate at an orthogonality math.
What is orthogonality?
Just like you.
So you want to start getting used to the ideas of fields, things you cannot see but that greatly affect the world around you. Like for example, look up a YouTube video of turning on a light bulb without plugging it in. You can turn on a light bulb with a Tesla coil.
I can turn on a light bulb with my mind.
Well, you can do it with a Tesla coil. That's because of the potential difference. We'll talk about that as the semester goes on. But we are going to start with a review of vectors.
They're not getting used to
Yes, you are. What'd you just say?
Wait, what did you?
I might have just said these big words are why I don't walk in. What you think?
Says the person who's not going to go to class in medical school.
Structures, man.
I'm not ever going to the doctor. I'm just not. I will try to find a veterinarian.
Are you really not going to show me?
Great help.
So we're going to do a slight review of vectors again. Okay, again, so here's a nice little way to start up. You see those lines going between the positive and negative charges? That's your electric field. One thing to start wrapping your mind around early is electric fields are going to go out of positive and into negative. And then, of course, at every single point on this field, let's say right here, Every single point is going to have an electric field vector. So vectors, we have two quantities we're dealing with, vectors and scalars. Scalars are just your numbers. Or scalars are going to be magnitudes of vectors, the size of the vector. The vectors are going to have both size and direction. And that's going to be important. Eventually, we're going to have to work on breaking vectors into components. Remember your so we're just going to be working in X and Y. Remember, your components are the part of the vector that exists in that dimension.
Georgia.
So for every vector, you're going to have an X component and a Y component. So of course, we have the notion of coordinate systems. The Cartesian coordinate system is the one we'll be using. Yeah, I don't think you're going to solve anything in polar coordinates, but if we're looking at the Cartesian system and we're talking about vectors in each one of these quadrants, remember when we solve vectors, we can use angles we'll talk about different angles we can use to solve, but the sign on the components is going to be important. You're going to have to set a positive and negative direction and stick to that. So it's like you could set positive Y, positive X. That means going the other way is going to be negative Y, negative X. And based off where a vector is, you know the sign of its coordinates.
I do.
Really?
Sorry.
I'm joking.
Okay, so remember in your first quadrant,
That's probably what I mean.
X and Y are both positive. In your second quadrant, negative X, positive Y. What about the third quadrant?
Negative, negative.
Negative, negative. And then the fourth quadrant.
Positive X, Y.
Positive X, negative Y. So as we're solving vectors, you're going to want to keep a watch on this because if, for example, let's say you use an acute angle to solve for your vector components, they're all going to come out positive. But if your vector's in the second quadrant, one of them has to be negative. So you're going to have to keep track of that. There is an angle you can use that will give you the correct sign on your components every single time. Does anyone remember what it is?
An angle you use?
Yeah, what angle can you use that?
360, like all the way around.
You guys are right there. So it's, first off, is the angle measured clockwise or counterclockwise? Counterclockwise from what?
Positive.
Positive x-axis. Any angle you have that's measured counterclockwise in the positive x-axis, you can use that, and that angle will give you the correct sign on your components every time.
All the way up to 360, right?
Yep.
Yeah.
Well, you wouldn't do 360 because you just go back to 0.
Okay, yeah. I see what you mean.
But most of the time, you're not going to have that situation. You're going to be making your right triangle, figuring out the angle, solving for the components.
Susie kind of forcing on me.
So, for example, I'm going to put a vector in here. So you remember, of course, this will make more sense as we go along. If this is your electric field, and of course you have the Y component, the X component, you're going to have to figure those out. When you're working on this, now you see how we made the right triangle there. So you may have that angle theta. If you use that angle, both of them are going to come out positive, but you know that the Y component has to be negative based off the fact that it's a fourth quadrant vector. Negative side, it's on the negative side of, it's in the negative direction of Y, pointing down. Because remember, plus X plus Y are set that way. Other angles you could use. You may get that.
The sixth thing.
And you remember your components can be on either side. Doesn't matter what side they're on. These are the components of that vector that live in X and live in Y. It'll make more sense as we go along. Your point P here, which you're going to do a lot with point. So remember, that's going to be, you can always find those with a direction, a position vector R. For those of you who haven't done vectors yet, this does become a lot more clear as we go through it. So, but just the whole point is you want to make sure you know your positive and negative directions, where you're going to have positive X and Y and where you're going to have negative X and Y, because that you will have to use that. Just to make sure we're staying consistent. The other two coordinate systems that things exist in are cylindrical coordinates and spherical coordinates, both known as polar coordinates. Now, you will see me use spherical coordinates, but I don't think you're going to have to actually, at least for the time being, you're not going to have to use it yourself. You're going to do everything in X and Y. Because for spherical coordinates, you need three dimensions. You need rho, theta, and phi. However, a lot of the laws that we used are solved from spherical coordinates because, of course, okay, why? Why would we use, and this is going to be an idea I want you to start wrapping your mind around before we even get to Gauss's law. Why would we solve so many things for an electric field from a spherical coordinate system? What's the sphere?
Earth.
No, not the Earth.
Electrons are circles.
Gravity.
I'm not answering your question. I forgot what the Greek symbol for rho is.
Oh, it's this P looking thing.
Wait, can you repeat the question?
Okay, so I want you to start wrapping your mind around spatial geometries for when we get to Gauss's law. Why would we solve a lot of electric fields and find a lot of laws for electric fields in spherical coordinates?
Because the earth is a
Think of it this way. Let's think of an electric field of what we call a point charge, a singular point that has a charge. How does it radiate? The electric field is a radiation from that particle. How does it radiate?
And circular.
Every direction.
Right, outwards in a spherical symmetry. So that's why we use this a lot. So if you're radiating from a single point, kind of like the center of mass on Earth, the gravitational center, it radiates out in a spherical geometry. But I don't really think we're going to use these too much. At least I haven't seen anything yet. Now, I do want to show you graphically what solving vectors looks like, even though keep in mind when you solve things, you're going to be using component forms. But we want to understand how this all works because, for example, does anyone remember what the sum of a bunch of vectors is called? Resultant vector.
Say it there.
Oh.
It does.
Yeah, looks like.
I also realize there's not a lot of people that read the slides.
I was just making eye contact.
Those are words. Now, the way this works, let's say we have vector A. Also pay attention. Do you see how I'm writing that with the little arrow over the top? That's your vector notation. Now, they might not always do that in your textbook, so pay attention because in a lot of physics textbooks, a bold letter is a vector. So if you see like your E and it's bold, and it's not italicized, that's usually their vector symbol. But it just depends. They might use the arrow symbol. I'm not going to have you draw out bold characters on your homework, so just use the arrow symbol. There is another way you can write vectors. However, if you use that format, I will make you tell me what that actually represents.
Not right that time.
Yeah, that's gonna confuse me. I'm not ready.
So yeah, just use the arrow symbol. I'm just letting you know things you could see in different sources. Okay. If you're ever on a website somewhere and they use that little bracket system, that's a vector. Okay, so just kind of just be like, oh, fine, that's a vector. But use the system with the arrow. Then let's say we have vector B. Now, what we want to know, our resultant vector is A plus B. And that, your resultant vector always goes from the tail of the first vector to the head of the last vector. So that means I started doing if I have all of those vectors, my resultant first off and it doesn't matter how many vectors you have, it's always from the tail of the first one to the head of the last one. So here's a fun one. Vectors are commutative. What does that mean? Yeah. So we could say if we had R equals A plus B, it also equals B plus A. Okay. We were asking this one on a quiz last semester, and a lot of people missed it. The negative of a vector. Okay, so what if I have so first off, vector A. Which component will be positive? Which component will be negative? Negative X, positive Y. Now, the negative of the vector is in what quadrant? Fourth quadrant. So remember, the negative of your vector is the exact same magnitude as your vector, just points 180 degrees in the opposite direction. And also keep in mind as we're going forward that the negative of a vector is essentially taking your vector with its components and multiplying by -1. So this is going to end up leading us into vector subtraction. So the first way we can look at vector subtraction, we can say, well, I have a vector A. Vector B. For subtraction, we're going to have some new vector C equals A minus B. And the new vector will go from the head of the second one, the head of the last vector, to the head of the first vector. That is the geometry for vector subtraction. But also remember that we said that the negative of a vector is essentially the vector multiplied by -1. So let's look at that vector B, because What's another way that I could write this subtraction? A minus B is also, what's another way I could write this? Yep, plus negative B. So what would that look like? Well, let's see. Well, we're still going to have vector A. Then you see that A is the exact same vector. B now is the exact same magnitude pointing in the opposite direction. So that's your negative B. And then if I took C here, still fits in there pretty nicely. And so now you see we've gone from the tail, the first vector,
Feel like in.
to the head of the second vector, or the last vector, and that's going to be your vector C. So since we've gone from the tail of the first vector to the head of the last vector, this is now a vector addition, but it's A plus the negative B. That's a quick overview of how this looks graphically. What we're going to be worrying more about is vector components. Okay. See how we. Okay, so I don't know. Let's throw in some vectors. I have some sizes on here. I'm going to try to get this right. It's Y, it's X. Okay. Same idea there. Let's take our first vector.
Yes.
We'll do vector A.
What are those? 2, 4, 6, 8.
Yeah, so I'm going to go out here.
You didn't know what you wrote. Don't laugh at me.
Up to there.
That's as far as I can count.
So that'll be our vector A. And then let's look at the components. So in this case, what is AX equal? 7.
Yeah, I was just telling that.
AY
I put 5, but that could be wrong.
it should be 6.
Close.
But we're getting the idea that this vector exists in both the X and Y directions. It has a part of it that exists in Y, has a part of it that's a magnitude that exists in Y, and a part of it that's a magnitude that exists in X. And we also know that based off positive or negative, that points a certain direction. So these component vectors, they also have both size and magnitude.
Oh.
We could look at, say, six. So here.
That 5. 6.
Dx is going to be, of course, a -6. And we'll get to directions here in a little bit. Your By, what is that? Right? But it drives home the point that these vectors that exist in multiple dimensions, they have parts of themselves that lie in X and lie in Y. Now, let's keep in mind some of the angles we could look at here. We might have angle theta. There's an angle phi. The angle that we can use that will always give us the correct sign. Angle gamma. And I'm just using whatever Greek letter I can. You could call them something else. I would avoid letters that show up in the actual theorems. Like I wouldn't use lambda for a whole lot because we use that for wavelength.
Can you draw gamma big again? I never remember. G, right?
Wow, whole 180.
No, but gamma's counterclockwise from the positive x-axis. Let's see,
To where? Just to that
Yeah.
B?
whichever vector you're measuring.
Oh.
So this one is to B.
Yeah.
We don't really need it for A because we have theta measured counterclockwise from the positive x-axis that gets us to A. I think I mentioned this somewhere else, but I just want to go ahead and view it. So you'll have problems that solve with positive angles and negative angles. Which way do positive angles go? Counterclockwise. If you have a negative angle, you really need to be looking for a counterclockwise motion. Positive angles, no. Did I do that backwards?
Negative goes clockwise.
Yeah, negative goes clockwise, but positive angles go counterclockwise. Negative angles go clockwise. So that's the best way to start. But again, as time goes along and you start calculating angles and positions of vectors, you're gonna get used to where they're at because you're gonna be able to say, well, I have an angle that's 30 degrees. I have a vector that has an x component of -9, y component of 3. So that x component is much larger than the y component. So that 30 degrees has to be the smaller angle. In this in negative x positive y would have to be the second quadrant. You're going to be able to analyze them that way. It'll make more sense when we're actually looking at problems that we're solving. Now, 4 components. You're going to want to bring back our trigonometry. Your components are going to use sine and cosine primarily. Your tangent will come in when we're looking for the direction that a vector is in. Okay, so now we're going to do a first quadrant vector to start with. The first quadrant vector, once you see how to solve it, also gives you the general formulas for the components. But remember, you can only use the general formulas when you measure counterclockwise from the positive x-axis. Otherwise, you're going to have to make the right triangle and analyze it. Let's put an electric field there, okay? We're going to draw in our components. We've made our right triangle, okay? Right triangle.
Yeah.
Now, y, the x, and we have an angle theta. Again, this will give you the generalized format for the vector component equation. Okay, so looking at the x component, which trig function do you think I want to use in y? Cosine. Why cosine? Right, because EX is adjacent to the angle theta. So again, it touches the angle theta, so it's adjacent. Y is opposite the angle theta because it's diagonal. So if we said cosine of theta Now, notice how I wrote the E without the arrow. That's called a magnitude. We'll talk about that in a little bit. Okay, so if you don't see the arrow, that is the magnitude of a vector. Talk about what that means. So if we wanted to figure out this component, EX, the magnitude of the electric field, cosine of theta. And your EY then and it kind of makes sense because the magnitude of that electric field is the length of the electric field vector. And that's the hypotenuse of your triangle. So that means that your Y component, magnitude of your electric field, is sine of theta. So you're basing this all off right triangles. Okay, we'll pick this up again on Wednesday, and we'll continue going through how vectors and vector components go. Again, if it seems confusing right now, if you've never done vectors before, it does start to make a lot more sense when we're solving actual problems because we're going to do it over and over and over.
I already went this.